Welcome back to educator.com. We have another lesson in intermediate C++. Today we're going to talk a little bit more about some typing that can be done with C++. We will discuss a few more types. Some are good to use, not so much. Some are just left over from C. There's a union which allows you to store different types of data in the same memory, which has a few issues involved, which we will talk about. So we'll talk about the cautions for those, and particularly platform dependency. So you think, I got this code, it's working beautifully on my PC at home. You go load it up to a Linux machine, and everything crashes. And particularly if you're depending on unions just for such. And we talk about the enum, where you get a list of constants that we can use. And we have a type def, which is a C legacy thing, which was kind of necessary. It's not as necessary in C++. Which allows you to create types from types, but you kind of have to know about it since there are things in C that you need to still use and still work with. So we'll have some cautions on that on the underlying type. We'll have some more detail on the const keyword, which we have already seen without actually just talking much about. And we'll have the const variables, const object methods, and an introduction to the mutable keyword. And so we're going to have some more kinds of C++ types. C++, if you don't know, it's a hybrid between, some folks say it's a strongly typed language, some folks, well, not really. It's kind of a hybrid between strong type and weak type. It's got some strong type conventions that you can use to let the compiler enforce type safety for you. But it allows some shortcuts for those in the know. Who's in the know, that's where it gets careful. So my personal recommendation, avoid the shortcuts. Let the compiler do its type checking job. Write your code in such a manner that the compiler can do type checking for you. Especially when you don't know what you're doing, you're new at this sort of stuff. It's real easy to make mistakes, but especially when you think you know what you're doing. There's a lot of people out there who think that we put a shortcut here and we can do a typecast there and we do all this wonderful stuff to circumvent the compiler's type checking, and the code will work for months and months and months until someone puts it somewhere else and everything crashes, or you load it on even on the identical same machine, just slightly configured differently, and everything stops working. So if a shortcut is necessary, use that shortcut with caution. The compiler type checking is there for a reason. Is to help you try to prevent you from shooting yourself in the foot. Double check your design. Make sure that the shortcut really is necessary. Because it might be there's a better way to do it using the compiler ways of type checking. So unions. One of the shortcuts is the unions. Well, I have this wonderful type. I got this wonderful double stuff out there, and I've got this integer. I've got whatever it is I want. I want to look at this particular byte out of this word. How do I do that? Well, we can do left shift, and we can do right shift, or we can just do a union and map that long integer onto a 4-character array, and then I just assign the array. So here we have a check bytes union that consists of two variables. We have the int, which is a 32-bit integer on most machines, and then we have the char, the bytes, which is 4 bytes on most machines. These two variables share the same physical memory inside the computer. So if you say the int is equal to this large number, and then let me take a look at byte 2, character 2, we'll print out the letter capital A, because this will be 65. So basically I worked out this number by adding in here A. And so that was 65 in that byte, 65 in that byte, 65 in that byte, 65 in that byte. And when that got interpreted as a 4-byte integer, this is the number that came out. It should be obvious this is not going to run the same way on different platforms. Like, you put this onto a 64-bit machine, and they say, hey, we've got 64 bits to play with. Let's make the int 64 bits. And while we're at it, we'll use UTF-8 and UTF-16 for our character set so that we can handle international characters. So we'll have the char be 2 bytes. They're allowed to do that. The only thing that they're required to do is make the size of char less than or equal to the size of short, less than or equal to the size of int, less than or equal to the size of long. If they're all 64 bits, they're following the specs. And then you have some code like this that won't work. So be careful with that. Keep that in mind if you need to do something like that. And you've also had other issues, big endian versus little endian. Not little Indian, little endian. And what you have there is on some machines where this is the 0th byte, and so you have your character array. So this is the same. Well, this is an integer. Let's say you have, well, let's make this one the integer like I started. And it's 4 bytes long. And this is our character array. On some machines, let's say we have this A, B, C, D. On some machines, it will put the A there, B there, the C there, and the D there. Other machines, being big endian, I forget, don't ask me which way is which. Just remember that on some machines, it'll put the A there, the B here, the C there, and the D there. Because that's just the way, it gets worse. There are some machines where it's big endian, little endian on a 2-byte basis. So it'll put the B there, and A there, and then the D here, and the C there. Wait, that's backwards. That's not what I wanted to do. So it's basically reversing 2 So we'll put the A here, and then the B there, and then the D there, and then the C there. And don't even talk about at the bit level. So just to keep in mind, we'll talk about word boundaries in a minute. We have additional issues with that. So I'm basically just introducing you to this so that you know it's there. There are uses for it. There are occasions where you have this big, huge structure and you want to store it in there and you have a need to inspect an individual byte. So you just union it to an array of bytes and you can access the bytes that way. But just remember, it's dangerous doing things like that. So typical use is before we had C++, you want to do something like polymorphism. So you have a union of structures. Our first structure will have a char that says what kind this particular structure is. So if we just grab some data from somewhere, we can inspect what kind. If it's 0, we'll use this. If it's 1, we'll use this. In this case, what we have is an integer as an employee ID, a 32-byte character name for the employee name, another 32 bytes for their address. Now, if it's 0, if what kind is 1, or even just use a character, then we have an E here. And we'll use a V for meaning it's a vendor. So now we'll have the vendor name and not even have the integer there. We'll have 32 bits for the vendor name, followed by the SKU for the particular product, and then the name of the product. And it's all stored in overlapping memory. You can have an array of these, where each unit now is actually a different object. And then finally, let's call this perhaps as D for data array, where you just want to grab each byte and look at each byte individually to inspect for Lord knows what reason. So here we have a use of it. We have myUnion.whatKind equals E. If it's E, then we will pass this to some function that handles employees. If it's V, we'll call some function that handles vendors, etc., etc. Now we have some union rules. The compiler allocates enough memory to hold the largest segment, which should be obvious enough. And there is no platform-independent way to store the member data such that you know that the data is a certain way. It depends on the platform. It depends on the operating system. For example, word boundaries. Here we have a structure between A and B. And you want to union that with something else. You figure, okay, well, this is going to be 5 bytes long, right? So you've got a character, and then we have a 32-bit, which is 4 bytes. So it's going to be 5 bytes, right? Well, not necessarily. Some machines, when they have an integer that says, our most efficient way to handle an integer is if it's on a so-called word boundary. So it'll put the byte there, and then you have your A here, and then there'll be 3 bytes of trash, which will be never looked at, and then B will be your integer. So that means the size there is 8 bytes. So, you've got chars and ints and doubles and structures and objects all mixed together. You have no way of knowing in advance on a platform-independent manner to find out exactly where things are stored. So on some platforms it's 5 bytes, on other platforms it's 8 bytes. So, and if you can store objects and classes, but if there's a constructor, the compiler won't let you do it because it doesn't want to have to be concerned with how do I construct this thing inside this union. And just think about how confusing that would be. You've got object A, and you've got let's put A there, and you've got object B, which is a totally different object. It's sharing the same memory. You call the constructor for A, and you set the memory a certain way, and you call the constructor for B, and you set the memory a certain different way, but it's the same memory shared by the other object. And both constructors are constructing the memory in such a way that's safe for their class, but not necessarily safe for the other class where you're sharing the memory. So rather than deal with those issues, the compiler says, no, if you've got a constructor in your object, you cannot put it in a union. Now, another type that we have is enumerators. It's useful for defining an enumerated constant. Like you can have constant integer Monday equals 0, Tuesday is 1, Wednesday is 2. Well, instead of doing all that, you just have days of week. It's Monday, Tuesday, Wednesday, Thursday, Friday, etc., etc. And then use it like any other type. So we can have days of week is returned from get our day. It passes some parameters. It can do some calculations. If this returns a Friday, and then we say, well, it's casual day, you don't have to wear your tie, etc., etc. Now, just remember the underlying type is int. It's not unsigned int, it's not short, it's not double. So you cannot use something like this and expect to get a 3.5. That isn't going to be there. And one of the dangerous things about it is it might seem convenient, but every convenience comes with a danger. It defaults to start at 0. And then you can just set something equal to 2, so there is no 1. It just skips over that. And then this will be 3, and then this will be 4. And then now we're starting back to 0 again. And where that's dangerous, it will allow you to cause overlap. So here we've got 0. So if there's something after that, it'll be 1, unless you say equal that. But if you're going to do all of this a lot, you might as well just do integer constants and just list them out and then give them whatever value. The best way to do that is to only have an equals on the first one, like 5. The default is 0. You don't have to specify it. And each one will be 1 after the previous one. And then don't worry about what the value is. Always use the variable. That's the whole idea behind having variables, so you can have something that you can remember and then let the computer turn that into a number and let the computer use the number. Otherwise, it can be used like a number. Because it is an integer, you can take my error code is equal to success, whatever that is, and add 100 to it. Okay, now I got my own error code is plus 100. But what if this happened to go all the way up to 100? Now you're overlapping again, so you've got some things to worry about. But the thing about it is less error prone than just having a list, variable, 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 this equals 1, this equals 2, this equals 3, this equals 4, blah, 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 blah. You're typing all this in, you're going to miss one, you're going to duplicate one, doing this. If you just set the first one and just go on, the compiler will automatically not skip any, it will automatically not duplicate any. But like I said, be careful with changing the sequence. Here I've changed the sequence. This causes an overlap. The compiler doesn't care. You want to overlap them, overlap them. But if you're going to set them all to 0, just set them all to 0. The whole idea is to have a sequence of distinct different numbers that you can use that for, like error codes, for example, or status codes, or whatever code that can be returned. You can test it. You can say, I have a missing parameters code, and you'll get a code back that is actually different from the found code. And it's also useful. This is not really a necessary part of it, but it can be useful if you write your code and you want some self-documenting to go on. You want to be able to print out error messages. Have a string associated with. So, like, let's say we have an alert here as an enum. There's a green alert, yellow alert, orange, red, and then have a string array that's associated with that. So we have the full text green, the text yellow, orange, and red. So now when you call your function, say get the alert, and your parameters determine what the alert level is. Do your calculations. You can return red. So when red comes back, you can either say if get alert equals red, then we got red alert. Dispatch whoever needs to be dispatched, or you can print it out for the user. Say alert level. You can now use your string array with the return, because this is an integer index. It is an integer. So you just print out whatever the alert text string, or an array of whatever the other objects you want to have that are associated with those enums, or you just put them all both into your own custom class and take care of it that way. Now in C, your types were created with the typedef keyword. In C++, there's not a whole lot of uses for it, because just defining the structure is defining a class, which is defining a type. So this is the way you would do it in C. You'd have typedef, define your structure, and you want to use a different word because you don't want to duplicate the same word, and the compiler won't let you. And you've got a 30-character name and an integer age, for example. And now there's your type. Person, you can now define a teacher. Person, teacher, the variable name, and initialize it to Alvin, and his age is 39. Sure, 39, really. In C++, instead of using a typedef, you would just define a class. Call it, say, employee, the string name, and an integer salary, and then have a public portion. All this is private. You'd have a bunch of other public methods for accessing the private variables, or you just make them public if you don't really need access controls. And so now you define an employee. So instead of having typedef structure blah 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 employee, you just have class employee. Or the difference between in C++, the main difference between a struct and a class is a struct defaults to public, class defaults to private. So you could just we can just do this right here. We can call this struct. Everything else remains the same. But in C, we didn't have this feature, so you needed a typedef in order to define a new type. That would be a structure or any other type of type. Probably the biggest use now in C++ is just type substitution. So you'll have a typedef keyword to create something that will be used in place of the underlying type. And the purpose is clarity for documentation or for change. It says don't use int for this type. Use this typedef that I defined, because it's int today. Tomorrow I might need to make it long. So here's our example. Here we have typedef. Float is the underlying type. The new type is age. Now there's a naming convention with this sort of thing. You'll have age underscore t, which is an age type. From other languages, you'll have capital T. You say this is now type of force, which is underlying type. It's float. Since this is C++, you can have objects, you can have classes, and you can have you can say typedef std : string is defined as capital S string. So now you don't have to have a using namespace std at the beginning. You just use this instead, and then use capital string for your string constants, your string variables. So here we have age t as the current age. The new birthday is a function that will say take this age plus 1 and returns the new age t. Now you happen to know that it's float. You could use this in float calculations, but the idea being that this is a new type, you should only use the functions that were defined with the type if functions were defined with the type. Here we have calculate tax, money t, receipts, and since they are all in this particular case, they're all floats. You can use them interchangeably. You could take the age and pass it into calculate tax. That doesn't make sense. but the compiler will let you do it. But the reason why you don't want to do that, for example, money T may be in the future be turned into a class. The class could include, like, this is currency. It's not enough to know that it's 39.5. Is it US dollars, euro, yen, etc.? All that can be made part of the class. Now, if you take the money T and you pass it into the new birthday, the compiler will give you an error. So keep that in mind, that you have the types. The types are there for a reason. To prevent you from doing incorrect calculations. You see, the compiler only checks the type def for the underlying type. It will not let you pass a float where it needs a string, for example. But one of the useful things, particularly in C, that allows you to hide the fact that something is a pointer. It may not be a good idea to hide that, but it's something that allows you to declare something, and it makes the code look a little cleaner. So you can do a type def that's useful in making a pointer to a type appear to be its own type. So, but don't be lulled to thinking it's not a pointer, and keep your type safety in mind. This example is a very good example from C. You have a linked list node. We'll call it LL node. It has a string name. Let's say it's got some data. It's got a height. It's got a width. And it has a pointer to the next node in the linked list. So now we have a type def defined, defined as a pointer to a linked list node. And to remind the user, yeah, we're letting you not have to put the asterisk in your name, but we're still going to call it PT to remind you, yes, this is a pointer to a node. It's not the node itself. So now we can define the pointer to the node as a header, is the header that will point to the first node of your linked list. And we will set its name. Maybe we have a new LL node. We'll set the name of the header to say this is the header node, and we don't have to set the height and width for it because it's merely a node that points to the first node. And then say header next will be a new, this is next. So now we've got a linked list with two nodes, and this one should be in your, if this was not a struct, you should probably have you can still have a constructor in here because C++ struct. You can put constructors and destructors inside your struct because it's just like a class. So you could have a constructor in here that says LL node and have it initialize everything, including setting that to null, so that you know your linked list. If your next is not null, there's a next node. You can traverse, go to the next one, go to the next one, go to the next one, until you get to one that's null, and at the end of my linked list. And so this is one of the ways of using type def. So now you can just declare it, and just makes your code look a little bit more Englishy, that type of thing. Now you have to be careful. You know that the type, because it's documented, it'll be in the header file. You can look it up. Oh, type def for this. Oh, that's just an int. Okay, I'll just use it like it's an int. You might think you know, because you might be looking at this particular header file that you looked up on the web, but the machine you're using is using a different header file because they've come up with a different type for that. Sometimes you have to use the underlying type because they just use time T, for example. You have an integer. That's going to be a 32-bit integer. That's an int. And it gives it to you as an int, and now you just use it like an int because this is left over from C, so there's no classes. There's no methods that you can call. It says give me next day. Let me call the next day method of the timeout. Here's the integer. This is the number of seconds since January 1st, 1970. That's the definition. This is the definition of time T. It's an integer, and that's all there is to it. It's an int, and most people treat it like it's an int, but at some point in time, this may become dangerous. So here's an example. We have time T now variable. Let me get the current time. I know this time T is an int. So I know tomorrow is now plus the number of seconds in a day. This is 60 times 60 seconds per minute, 60 minutes per hour, 24 hours per day equals this number. So now is right now, tomorrow is right now plus 1 day. If you're going to actually do this correctly in an more object-oriented way, you'd have a class that says get tomorrow, get today plus some number of days. Give me you have a date class, for example. So here's where it's dangerous using the int. It's a well-known problem that the 32-bit integer will run out in the year 2038. Your number will get to a certain point, and it will just wrap over to the next one. So suddenly, instead of being April 15th, 2038, it will be some year in 70 years earlier, or 100 and something. I haven't done the arithmetic. We should work that out, just what that number will be. Some people suggested changing it to a 64-bit int. Other people suggested using a structure that will include the number of milliseconds, the number of microseconds, the number of clock ticks on your computer. I kind of agree with going to 64-bit int, but there's no predicting what the future will bring. If they decide to make it a structure or a class, if you're using code that says give me today plus tomorrow to get to the next day, that code's going to break because you're not going to be able to just add something to it, unless of course they make a overloaded operator for it, which would be a smart idea, so that people who've been using it like an int can continue to use it like an int. But basically, if you're going to define your own type T, your own type def to create a new type using some underlying class, also provide your callers with classes to do the various things that they'll need to do with it, so they don't have to use the underlying type. So when you work with a type def, treat it like it's a class object. Provide your callers with any needed functions. So that allows you at some point in the future to say, well, we need to expand, we need to change, we need to add stuff to it. You'll be able to do it. Or just use classes. Don't use a type def at all. Just here's a class. Using a type def gives you kind of a shortcut. So here's an int that means age, or here's a float that means money. And you can do whatever you want with it, just like it was a double precision number. But remember that it is a money type. But if you do that though, if at some point in the future, well, we need to add, like I mentioned earlier, the currency. Is it dollars? Is it euro? Well, now you've got a future expansion problem. It's not a big problem for most people, but it's something to keep in mind. Now we've seen const. When you talk about constness, we use it quite a bit. Where you say we'll have a variable const, which I can't spell for the life of me. Look at that, C-O-N-S, and it's right there too. So it's like a const integer max rows, for example, equals 7, whatever it's going to be. So you know, and I know, that means that the compiler will prevent me from changing max rows. But it's more than just for variables or a parameter that can be changed on a function. You can also put that on a method to tell the compiler, this, and to the users who call it, this particular method does not change the state of this object. So for example, we have a class myObject, and we have a couple of attributes, integers, a and b, and then we have a public method here called print, and it's declared to be constant. This says to the compiler, it says to the users, the print is only going to print the variables without changing them. And then we have some other method, it's also constant, which is we're not going to change it. Don't worry, you can safely call this method without changing state. So if we print to see out this particular object, it prints 10 and 12. We call some other method, it's not allowed to change a and b. So if we print again, we should still see 10 and 12. Now if you don't put the const on there, let's say we have some other method, and you don't put the const on that. Now if you call that, you can call print again, and you might discover that a and b have been changed because it's not the method did not promise to not change, and since it didn't promise, it might do it. So we can put that on object members. So we have a table row. Here we have a table row, we have an identifier which cannot be changed. Once you've gotten this table row, once you've identified it, you've put the identifier, you cannot change it ever again. So here's a public. The only way you can set it is in the constructor. Even if you provide a method that says we can change it, you won't be able to change it because you've defined it to be constant. So we have a table row. New row is 17, some data. This row is permanently identified by 17, which is a better way of identifying this row. There's all sorts of other types of identifiers. Like, for example, you might have, let's put the social security number of the person in there. Well, the person might call you up later and say, hey, you remember that social security number I gave you? Well, I gave it to you wrong. You transposed the last 2 digits. Well, okay. Internally, you are identified by our identifier. So your social security number is just an attribute. We can go in and change that if we need to. And that's where your keyword const comes in. Now, that causes some problems. There are occasions when you want something to be constant, but you want to change it. So that's where you have the keyword mutable. Mutable means this particular attribute is allowed to change. So you can have a method that's defined to be constant because it's logically constant, like print. I'm just going to print the data. I'm not going to change the data. I'm going to print the data, so I'm defined to be constant. Now you want to say, let's suppose you want to say, well, how many times did the person call print? Let's put a member object there called count print. But you have to put the mutable keyword on there, which will allow you to increment that particular variable. So if a method is supposed to be constant, it promises to programmers and to the compiler to never change any of the object members, but some members may need to change. What do we do? Well, look at this, I misspelled change. And the word processor didn't catch that. So the answer is the method is logically constant, but certain data members may need to change without violating the logical constancy of the method. So a couple of examples is you want to count how many times that particular method gets called. There's another example is you have a time-consuming process. You want to cache the data. So if that method is never called, you never have to go to the database. But if it doesn't get called, we have to go to the database. That takes some number of seconds, takes some number of minutes, bring the data in. Now we just want to keep it in memory. So we'll call that mutable. And so the second time it's called, we don't have to go to the database again. Hey, we've got it right here in our cache. We'll just give you what we got the last time. So we'll do our calculations, whatever those calculations are, and then save the information internally in the object. So here's a couple of examples. We've got my class, we have an integer a, double b, and our mutable p count. We want to count how many times we print. And then we've got our print, which is defined to be a constant. And so the print says, I promise you, Scout's honor, I am never, fingers are crossed, I'm never going to change anything except for my one mutable variable, which I'm allowed to change, so I can count how many times have this particular item been called. And our other example, we have an employee with a mutable string name. And the get name is constant. It will get it, but it's not going to change it. It's just going to get it. But what it will do in part of that getting, the constructor, let's say the constructor has set it to UKN or has set some flag. That's another thing that you might want to set to mutable. It says, let's say we have a mutable Boolean is set. And the constructor could set it to false because it has not been set yet. And so the first time this method is called, if the name is equal to UKN, or alternatively, if isSet is false, there's, oh, we need to find out what this person's name is, so let's call the database, get the employee's name, get whatever other information that we have on that employee, and just go ahead and get it. And then now that we've got it, it's no longer set to UKN, or set isSet to true, and then just return the name. Because now the name is known, so every other time it gets called, we have the answer. We can provide the answer more rapidly. And we have some union troubles with a very bad joke, but the best one I could think of. Well, anyhow, that's it for today's class on C++ Intermediate. See you next time at educator.com.